This is SpaceTime, Series 28, Episode 136, for broadcast on the 19th of November 2025. Coming up on SpaceTime, the oldest Australian rocks offering new insights into the origins of the Earth and the Moon, tantalizing signs of a possible fifth force in nature, and satellites record 20-metre-high ocean waves on the Earth's surface. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have opened a new window into the origins of Earth's ancient mantle and continents. The findings, reported in the journal Nature Communications, are also providing fresh insights into the early beginnings of the Moon. The authors reached their findings by analysing ancient feldspar crystals within the oldest magmatic rocks ever found in Australia. They examined 3.7 billion-year-old anorthosites from the Murchison region of outback Western Australia. Now, these are the oldest rocks on the Australian continent and among the oldest on the planet. The study's lead author, Matilda Boyce from the University of Western Australia, says the timing and rate of early crustal growth on Earth remains a contentious issue due to the scarcity of very ancient rocks. Boyce and colleagues use fine-scale analytical methods to isolate the fresh areas of plagioclase feldspar crystals which record the isotopic fingerprint of the ancient mantle. The results suggest that the continents began to grow relatively late in Earth's history, from around 3.5 billion years ago, which is around 1 billion years after the planet formed. The study also compared these results with measurements of lunar anorthosites collected during NASA's Apollo missions. Boyce says anorthosites are rare on Earth but common on the Moon. She says the findings are consistent with the Earth and Moon having the same starting composition around 4.5 billion years ago. Boyce says it supports the idea that a Mars-sized planet, which we now call Theia, collided with the early proto-Earth, melding both bodies together into a magma ocean, and ejected debris from that impact event, eventually coalescing into orbit to form the Moon.
The question that we wanted to address is looking into when the earliest continents grew on Earth. And one way of doing that is to look at the chemistry of the mantle through time, because the Earth's the only planet that we know of that has plate tectonics, and it's really been quite integral in, the development of life on Earth and all the other really unique aspects of our planet. But looking at old mantle-derived rocks is quite difficult because we don't have much left preserved from that time period. But in Australia, and particularly in Western Australia and in the Murchison region, we've got some of the oldest rocks on Earth. These are the oldest rocks in Australia, 3.7 billion years old, and also some of the best preserved of this age. So what we were doing is looking at these magmatic rocks that formed from mantle-derived magmas, probably underneath an early ocean, and looking at the chemistry of these rocks, and then looking at how the mantle composition changed through time.
Was it the Jack Hills area? Can I describe it like that, or is that overly simplistic and too broad?
Very close to the Jack Hills,
okay.
So all around those areas. It's beautiful country. We took vehicles from the Geological Survey and we camped out there, myself and my PhD supervisor, for a couple of months over a few field seasons, and camping out in swags and looking for these old rocks. A type of rock called anorthosite. So it's a rock mostly made of plagioclase, and they're quite uncommon rocks on Earth, but they're actually what makes up most of the lunar crust, which is quite interesting.
But they're fairly rare on Earth.
That's right. They formed in slightly different ways from the lunar ones, but they're quite interesting. They're very distinctive. They've got these enormous round crystals, white crystals, the old Earth ones. So they kind of stick out when you see them walking around in the Murchison. There's not much rock exposed. It's quite dusty and kind of low scrub, and then you see these kind of big crystals sticking out. They're quite unique looking.
What did that tell you about the age of the continents?
So the techniques that we were looking at radiogenic isotope systems, particularly strontium isotopes and calcium isotopes. And the way that these work, you can use it to date rocks. So for young materials like fossils, carbon dating is quite a well-known technique. And then for very old things, we can use things like uranium, lead, or strontium. But the other useful thing with these radiogenic isotope systems is that given that we know how long that these systems decay, the half-life, we know that quite well. We can actually, knowing the age of the rocks as well, we've already dated them, we can get this sort of fingerprint of the rock from when it crystallized. And because these are mantle-derived rocks, the fingerprint that we measure in these rocks gives us the composition of the mantle. So if we look at a range of these rocks, if we know that they're well preserved and we've been really careful to select the best preserved materials and target them quite carefully, which is what we did, we can look at how this mantle composition changed through time. Because when the Earth when it first formed, it would have been fairly uniform. Before we had these continents, it would have been mostly just a primitive mantle, is what we call it. Then as the crust grows, as the mantle is melted and as magmas come out, certain elements go into those magmas preferentially, which means that actually the composition of the mantle gradually changes through time. So that's what we're looking for. What we found from these rocks from the Murchison, these really old 3.7 billion year old anorthosite, is that the mantle composition was close to that of the bulk Earth, which means that there hadn't been much continental growth at all by that stage. But then what we found through time, so coming into 3.5, 3 billion years ago, we start to see this crustal signature emerge, which is what we call a depleted mantle signature. So what we found is that actually the growth of these continents, it didn't start straight away. It took quite a bit of time. So the first billion years of the Earth's history or so, there's probably not a whole lot of continental crust around at that stage.
So the crust was formed as this convection took place in the mantle.
That's right, yes.
Yeah. And the lighter materials stayed on the surface. That's where we get a lot of our granitic rocks.
That's right. And on the modern Earth, we know quite well how these processes form. We have these plate tectonic systems operating with continents growing and then oceanic crust getting subducted and destroyed. But in the early Earth, it might have looked really different. And we don't really know. There's lots of theories, but we don't know for sure whether it was a process similar to modern plate tectonics or something completely different. And probably the Earth looked very different to how it did today. It would have had a lot more ocean, a lot of just low-lying basaltic lava. And then probably from about the 3 billion year ago mark, it started forming granitic continents and large stuff from the ocean. And then that became kind of more exposed and started becoming a bit more like the modern Earth over time gradually.
How did you do the analysis?
So we already knew the age of these rocks by uranium lead that had been done previously, actually back in the 80s and 90s. But what we did with our strontium isotopes, because these rocks they're very old, they've been buried at depth and brought back up and fluids have gone through them, they've had a really complicated life. So we had to be able to target the domains that were fresh and preserved their magmatic compositions really precisely, quite a high spatial resolution. So what we did, we have a system that's called laser ablation mass spectrometry. So we have a mass spectrometer which is able to measure isotopes of the same element, so different masses of the same element, and then we can look at the ratio of that. And that's hooked up to a laser system. So we can go at quite a fine scale in these crystals, which was imaged via various different microscopy techniques. And then we look with this laser and we can ablate quite small areas of these crystals out and then put that through a mass spectrometer. So we did both that. And then we also used essentially a dentistry drill, and we drilled out slightly larger sections of these fresh crystals and we dissolved them up. This was done actually at the University of Bristol in England. So we used this little dentistry drill and drilled out the fresh bits of these crystals, and then we dissolved them up in acid and purified them. So we just had the elements that we wanted to analyze. And then again, we used a mass spectrometer for that. So really the key with these techniques is that you have to find, with these really old rocks that are super complicated, the best preserved areas that you can and then target them really carefully and precisely. So that's what we did.
There's a lot of debate about when plate tectonics began. How does your research go towards resolving that? It's
a very kind of contentious topic and there's a lot of debate around that. And there's one school of thought that kind of argues that these processes began almost immediately. So the Earth formed 4.5 billion years ago, and then straight away we started forming all of these large continents. From our study, we think that it took a little bit longer to start. And the system that we've used, these strontium isotopes, it's not an approach that's been used before, but actually it shows a very similar result to other isotope systems that have been previously applied to different types of rocks. So it kind of ties in and it agrees with these other results from different studies. Our point of view is that it probably took a little bit longer for these processes to really get going, plate tectonics. We might have had something sort of similar to plate tectonics, but not exactly the same. But it started beginning, and it probably was a bit of a slow transition.
I would have thought plate tectonics triggered the formation of the continents, and you couldn't have continents unless plate tectonics was already happening. Am I right there? Or
There's actually lots of other theories of other ways to make continents without plate tectonics. That's right. Yeah. So there's all sorts of names. Some researchers think that a process called sagduction. So we talk about plate tectonics as being like plates are moving laterally, but there could have been some sort of vertical system that instead. So what that would mean is that we've got all of these lavas coming up and melting, and then they start forming these kind of thickened platforms or plateaus. And as these get thickened and thickened from gradual eruptions of more and more magmas, it gets hot enough at the base of these big piles to actually start melting and forming granitic magmas. So that's one method that could have made these early continents without plate tectonics.
Is that what we see in cratons and hotspots?
That's what we see particularly in the Pilbara of Western Australia and the northwest of Western Australia. That's probably one of the best examples of that, of how continents formed early on without any clear evidence of plate tectonics. That's right.
Are you looking forward to the return of humans to the moon? Because that's where the oldest rocks on Earth have been found.
Absolutely. And it's been suggested previously that the best place to find possibly this kind of Hadean record from the Earth is on the moon itself, because we've got ancient rock from the moon that we found on Earth as meteorites. And why couldn't it go the other way around? Why couldn't we have meteorites from the Earth sitting on the lunar surface? Which I think is a really interesting idea. In terms of the studies that we did here with these Earth rocks, we did a comparison with these ancient lunar rocks. And because there's no plate tectonics operating on the lunar surface, the ancient crustal record of the moon, these really, really old rocks that formed not long after the moon formed itself, have just been sitting there on the surface, and they have been impacted by meteorite impacts, so they've been crushed up a bit, but we have this quite unique record from the moon that we don't have from the Earth from this early period. So I'm very excited to see what future materials get brought back from future missions, for sure.
That's Matilda Boyce from the University of Western Australia. And this is SpaceTime. Still to come, scientists may have found the first tantalizing hints of a possible fifth force in nature. And satellites record 20-metre-high waves on Earth's oceans. All that and more still to come on SpaceTime. Scientists may have found the first tantalizing hints of a possible fifth force in nature. A report in the journal Physical Review Letters claims physicists using 5 calcium isotopes tracked how electrons leap between energy levels in excited atoms. These jumps reflect the shape of the nucleus, and they should also align in a smooth curve across isotopes, known as a king plot. But the thing is, they didn't. Instead, they consistently revealed a subtle, persistent deviation, which could be a sign of a so far hypothetical force particle dubbed the Yukawa boson. Now, if accurate, the new particle would have a mass of somewhere between 10 and 10 million electron volts. And that would change the standard model of particle physics, which is the foundation stone of science's understanding of the universe. The model describes the 17 elemental particles that make up the cosmos. These include 6 flavors of quarks and 6 types of leptons, including electrons, muons and taus, as well as 3 flavors of neutrinos. Also, there are 5 force particles called bosons. These include photons, which mediate the electromagnetic force, gluons, which mediate the strong nuclear force, that's the one that holds protons and neutrons together, and the W and Z bosons, which mediate the weak nuclear force that causes radioactive decay. These are known as gauge or vector bosons because they have integer spin. Then there's the Higgs boson, which gives particles their mass through an all-pervasive Higgs field. It has 0 spin and is described as a scalar boson. The only force particle yet to be discovered is the hypothetical graviton, which, if it exists, has an integer spin of 2 and mediates the force of gravitational interaction. And like the photon, the graviton is thought to be massless. The problem is there are many things the standard model of particle physics can't explain, such as the full theory of gravitation, or the existence of dark matter and dark energy, or for that matter, why there's more matter than antimatter in the universe. Some promising theories predict the existence of a new fifth force of nature, alongside the 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear force. For instance, it's thought that some unknown force could exist between neutrons in the atomic nucleus and electrons in the atom shell. And this force could be carried by a new particle similar to how photons carry the electromagnetic force. Physicists normally conduct experiments using particle accelerators, such as CERN's Large Hadron Collider in Geneva, to search for new particles beyond the standard model, to try and explain these outstanding problems. That's how they found the Higgs boson. But physicists from the ETH Institute in Zurich took a different approach by searching for a new force between the neutron and the electron, using precision atomic spectroscopy to measure atoms with extremely high levels of accuracy. One of the study's authors, Luca Hober, says if this force really does exist in the atom, then its strength would be proportional to the number of neutrons in the atomic nucleus. So, by experimenting with various isotopes, the authors hope to detect this hypothetical force. Isotopes are types of the same atom that differ only in the number of neutrons in the atomic nucleus. This means that isotopes have the same number of protons and electrons and are therefore chemically identical, but they each have different masses. As a result, the total force experienced by the electrons in different isotopes should vary slightly due to the different numbers of neutrons. And this can be measured by examining the energy levels on which the electrons move within the atom. So the authors expect the new force would cause a slight shift in the energy levels between different isotopes. And they can determine this energy shift by measuring the frequency of the light emitted when isotopes transition between two different energy levels. This measurement requires an ion trap, where electromagnetic fields hold a single charged isotope in place and a laser beam then excites it to a higher energy state. The authors use 5 stable, singly charged calcium isotopes, each containing 20 protons, but with a number of neutrons ranging from 20 to 28. They were able to determine the shifts in energy levels of these isotopes with an accuracy of 100 millihertz, which is 100 times more precise than any previous measurements. They trapped 2 isotopes at the same time in the ion trap and then measured them together, allowing them to reduce the interfering noise during the frequency measurement. While the Zurich experiment looked for singly charged calcium isotopes, researchers at the Physikalische Technische Bundesanstalt in Braunschweig used the same isotopes but in a multiply charged state. The German group measured a different transition in these highly charged calcium ions, but with similar accuracy to the Zurich team. And a third group, this time at the Max Planck Institute in Heidelberg, measured the ratios of nuclear masses between these isotopes. All in all, the authors found that existing models could only explain part of the deviation. Another possible cause is the little studied area of nuclear polarization, a type of deformation of the atomic nucleus caused by electrons. Calculations showed that nuclear polarization could be large enough to explain the measured nonlinearity within the limits of the standard model. The findings are important because they provide boundaries on the possible values of the mass and charge of this hypothetical particle which would be transmitting the new force. So the authors are now working to further improve the accuracy of their results by measuring a third energy transition in the calcium isotopes. That will allow them to expand the King plot from 2 dimensions into a 3-dimensional diagram, and that could help them overcome existing theoretical challenges and make further progress in the ongoing search for this new force. Needless to say, we'll keep you informed. This is SpaceTime. Still to come, satellites record massive 20-metre-high waves on the Earth's oceans, and later in the science report, a new study warns that global carbon dioxide emissions are set to rise again this year. All that and more still to come on SpaceTime. It's been revealed that during recent storms, satellites recorded ocean waves averaging nearly 20 metres high, the largest ever measured from space. Moreover, the satellite data is now revealing that ocean swells act as storm messengers. Even though the storm itself may never make landfall, its swell can travel vast distances and bring destructive energy to distant coastlines. Driven by wind, waves are at their most powerful during storms. Yet the greatest threat to coastlines often doesn't come from the storm itself, but from the long swells that carry wave energy far beyond the storm's reach. These long waves radiate across oceans, and their properties, such as wave period or the timing between crests, reveal the storm's size and strength. For example, a 20-second period means a large wave arrives every 20 seconds. To shed new light on storm waves and ocean swirls, scientists combined data from the relatively new French-US SWOT satellite with the CCI Seastate Project's decades-long record, which incorporates measurements stretching all the way back to 1991. This record merges data from satellites such as SORAIL, JASON-3, the Copernicus Sentinel-3A and 3B, as well as the Sentinel-6, Cryosat and CEPHOSAT. Scientists not only confirmed the exceptional nature of storms in 2023 and 24, but also focused on the scale of swirls in remote ocean areas, measuring the properties of waves in storms before they become swirls. They analysed data from the SWOT spacecraft collected on the 21st of December 2024 during the peak of Storm Eddy, the largest storm in terms of average wave height over the past decade. And it generated a new record wave height of nearly 20 metres in the open ocean. Beyond measuring the wave height, the authors were also able to track the storm's swell radiating across more than 24,000 kilometres of ocean, from the North Pacific through the Drake Passage all the way to the tropical Atlantic between December the 21st, 2024 and January the 26th this year. The new findings, reported in the journal and the Proceedings of the National Academy of Sciences, are the first to directly offer observations which validate numerical wave models in extreme conditions, in the process correcting existing wave energy calculations. Now, scientists had long believed that very long ocean waves carried substantial amounts of energy as they propagated across ocean basins. But these new findings also demonstrate that the energy content of these waves has been systematically overestimated. This means that more energy than expected is actually concentrated in dormant storm waves rather than being distributed among the longest waves. The model shows that the highest waves of the past 34 years occurred in January 2014, when Atlantic storm Hercules produced 23-metre-high waves which caused severe damage from Morocco through to Ireland. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with the Science Report. New data from the CSIRO's 2025 Global Carbon Budget Report suggests that carbon dioxide emissions are set to rise again this year, and that the limit warming of 1.5 degrees Celsius could be reached within the next 4 years. It found global carbon dioxide emissions from fossil fuel use are projected to rise 1.1% this year, with CO2 concentrations in the atmosphere set to reach 425.7 parts per million. However, the report also shows that CO2 emissions from human activities, that's the sum of fossil and land use change emissions, have grown more slowly in the past decade at just 0.3% per year on average, compared to the previous decade's 1.9% per year. Even better news is that emissions from land use change are predicted to actually drop this year. The annual CSIRO report provides an estimate of carbon emissions from key sources, broken down by sector and country, and provides an assessment of the strength of natural carbon sinks such as forests and oceans. It suggests that land carbon dioxide sinks are set to recover to pre-El Niño strength this year, following a strong decrease last year. A new study has shown that vegan diets could cut global carbon dioxide emissions by 46% and land use by 33%. The findings, reported in the journal Frontiers in Nutrition, looked at weekly menus for omnivores, Mediterranean, pesco-vegetarian, ovo-lacto-vegetarian and vegan diets. Each plan featured equal energy values and followed international nutritional recommendations delivering all the essential nutrients. The authors found that vegan diets reduced carbon emissions by 46%. They reduced water use by 7% and land use by 33%, while the two vegetarian diets cut carbon emissions by up to 35%. All three plant-based diets were nutritionally balanced, except for small deficiencies in vitamin D, iodine and vitamin B12, which can all be remedied with supplements. The findings show that plant-based diets are as nutritious and healthy as a Mediterranean diet, but are much better for the planet's health. A new study warns that Australia's invasive cane toad infestation is continuing along its relentless march across the country and is now anticipated to reach the Western Australian Pilbara region within the next 10 to 20 years. The plague began when Queensland sugarcane farmers imported native South American toads from Hawaii. That was back in 1935. They were introduced to combat an outbreak of cane beetles which had been impacting local crops. But the toads quickly ran out of control, wiping out native species due to their poisonous glands and spreading far beyond the tropical cane fields where they'd been introduced. They now cover all of Queensland and northern New South Wales. There are even some occasional outbreaks seen as far south as Sydney. Towards the west, they've spread throughout the Northern Territory's top end, including the wetlands of the World Heritage-listed Kakadu National Park. And they spread across the territory border into the Kununurra region of Western Australia. The new research by scientists from Curtin University predicts that without containment efforts, the toxic amphibians will colonise up to 75% of the Pilbara region within 3 decades. The findings, published in the journal Scientific Reports, warns that the cane toads will cause widespread losses among native species, including native marsupial predators like northern quolls, ghostbats and kaluka, as well as frog-eating snakes, blue-tongued skinks and goannas. Samsung will release their new Galaxy Z trifold cell phone next month. Fully opened, the new phones will have a widescreen aspect 10-inch display. But they will be hugely expensive. With the details, we're joined by technology editor Alex Zaharov-Reutt from TechAdvice.life.
Well, this is Samsung's trifold phone, and look, it was on display at the big APEC event. It's still not official to the public, but obviously if you're allowing journalists to take photos of it from a distance on a stand, well, it's clearly going to come now. A report in Forbes said it was going to be US $3,000. There'd be only 30,000 of them made to start with. And I mean, over $3,000 is like over $5,000 Australian. So this is not going to be cheap. Apparently it will be 4.2 millimeters thin when unfolded. But that would make it at least 12.6 millimeters when it's folded together as a phone. Clearly, when you've got a device that opens up into a 10-inch smartphone, but still so thin, you're not going to have the same capacity of battery as, say, an 11-inch Samsung tablet would have. So the battery is meant to be 6,000 or 7,000 milliamp hours. It's still not fully 100% confirmed. And if it is the same thickness as the current Samsung Galaxy Fold 7, that also means no stylus technology. So this is Samsung's first such design that will make it to retail. They have showcased such trifold designs at display shows in the past, but they've never been able to be commercialized. And they were display technologies that looked cool. So look, the phone's going to be expensive, won't have a stylus, won't have as big a battery as a traditional tablet. They're going to make only 30,000 of them at first to test the market. They don't want to have to sort of say they're going to cancel it, just like they have done with the Samsung Galaxy S25 Edge due to not too many sales. And so, therein lies sort of the conundrum. Huawei is not the second generation such device, but the first generation from Samsung is still to come on December 5th. And the question is, how expensive will it ultimately be for Australians and those in the US, and how many people will be able to afford it?
That's Alex Zaharov-Reutt from TechAdvice.life. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.